Now that we've learned some things about probability, let's work a problem that uses some of these concepts. In this problem, we have the results from a test for marijuana use, and the results are given to us in a 2x2 or a two-way contingency table. And so I'm going to draw that here. Okay, so what we have are here the results from whether or not the person actually used marijuana, and the choices there are yes, they did, or no, they did not. And then we have, let's see, whether they tested positive for use of marijuana or negative. So these are the test results on this side. Okay, so here's what we know. 119 people had used and tested positive. 24 people had not used and tested positive. 3 people had used and tested negative. 154 people had not used and tested negative. So, let's think about our sample space here. There are 4 possible outcomes. The person, I'm going to do some abbreviation here. You could have a person, yes, they used and they tested positive, so someone who falls into this category. Or, no, they did not use, but they tested positive. Or, yes, they used, but they tested negative. Or, no, they did not use, and they tested negative. So those are the possible outcomes for each individual person that has this test run. Okay, so in order to determine these probabilities, we really need to know one thing that's going to be important is, well, how many people were we talking about? Because remember, how many times was this procedure repeated? So we need that number. So we can add across here 119 plus 24, it's 143. 3 plus 154, 157, and we get 300. And then let's add these columns here. See, that'd be 178, and this one here would be 122. And just to check, 122 plus 178 would also give us 300. That should add up horizontally and vertically. Okay, so now I might ask, of these 4 outcomes, which of these outcomes represents the correct results? So correct results for this test. Well, it's correct if a person uses and they test positive. So a yes positive would be correct. Or another correct result would be that they did not use and they tested negative. So a no negative would be correct. But of course these tests aren't 100% correct. So we can have incorrect results. And the outcomes that represent incorrect results are that the person used but they tested negative, or the person did not use and they tested positive. Okay, so obviously any lab that's running these sorts of tests would like to have this as small as possible, but it's just not realistic to assume that they can be 0. The probability that either one of these happens is 0. Okay, so just for interest's sake, let's find the probability of each outcome in our example here. So we want to find the probability of yes, they used, and they tested positive. So how many different ways, or how many times did we get a result of yes, they used, and they tested positive? Well, that happened 119 times, out of how many different people were tested? 300. Okay, so 119 over 300 gives us 0.3967, and I did round that to the 4th decimal place. Okay, then we've got the probability that the other correct result was no, they did not use, and they tested negative. So there were, how many people does that had that result? No, they did not use, and they tested negative. 154 people fit in that category out of a total of 300 people who were tested, and that result is 0.5133, again rounding to the 4th decimal place. Okay, I'm going to have to scoot this up a little bit. Okay, our incorrect results, one of them was yes, they used marijuana, but they tested negative. So there were 3 people in that category. Yes, the intersection of the yes column and the negative row, that's where we find these people, 3 out of 300, which is 0.01, and that's no rounding needed. It terminated at 2 decimal places. And then finally, the probability, the other incorrect probability or outcome was that no, they did not use, but for some reason the test said they did. And there were 24 people in the intersection of no and positive results. 24 out of 300. And that terminates at 2 decimal places. Okay, so now we have all 4 probabilities. These are not equally likely outcomes, as we can see. Something else we learned was that the sum of the probabilities in a sample space should equal 1. So let's check that. We add these up. 7 and 3 is 10, carry a 1. And that's 7 and 3, another 10. 9 and 1 is 10, 11, 12, and 8 is 20. And 5 and 5, that makes that 10. So it actually does add up nicely to 1. But you can see that if my rounding had been such that I ended up with 1.0001, that would still be okay, or 0.9999, just because of a little rounding thing difference. That would have been fine. Okay, so the sum of the probabilities of our sample space equals 1. We found our probabilities. Notice they're all between 0 and 1 inclusive. We said that they would be a ratio. Here they look like ratios, fractions, and they are numbers between 0 and 1 inclusive. So they could be 0, they could be 1, but as we see, none of ours were certain events or impossible events. Okay, and then another thing we mentioned was that we consider an event to be unusual if that event has a probability less than or equal to 0. So looking at our events here and their probabilities, we note that the probability that someone used marijuana but tested negative, it didn't show up in the test that they had, is 0.01. This event is unusual because 0.01 is less than or equal to 0.05, and that was our cutoff, the 0.05. So this would be an unusual outcome of this test, that someone did use but tested negative. It didn't show that they used. Okay, however, the other incorrect result is not unusual. This 0.08 is greater than 0.05, and so it would not be unusual for someone who did not use marijuana to get a result back that said that they did. Okay, these are important things for a lab to have on record and to try to work with. Obviously, they want these to be as small as possible because they want to claim that their results are really good. They get hired by companies to test people, employees or people in in rehab or something like that, and they want to be able to claim that they have good test results and that they can be trusted. So you can see here that this is how you would go about doing that calculation, and that sometimes you do get something that would be acceptable, something pretty unusual here, 0.01, but the 0.08 is not so unusual. This would probably send the person back for a second test. Since they did not use and tested positive, more than likely that person would have to have the test run again. Okay, so we've kind of summarized what we've learned thus far about probability, and we've also seen something new in this contingency table, a nice way to organize your results and make it very visual when you're selecting your values for your probabilities. Okay, I'm adding on a correction here because at about the 8-minute 45-second mark, you heard me say that we consider an event to be unusual if its probability is less than or equal to 0. Clearly that's not what I meant, and it doesn't make any sense. So let's make that correction. We say that an event is unusual if the probability of that event, we'll call it event A, is less than or equal to 0.05 or 5%. And that's the number we need to remember.